All right, so a few things I forgot to mention last time. So the first one is that the W that we discussed in the framework of Hamilton-Jacoby formalism is called Hamilton characteristic function. Okay, Hamilton characteristic function, while the entire thing S is called Hamilton principal function, but we also know that it's the action itself. Okay, so now I would like to discuss the spherical coordinates. Okay, and specifically I would like to discuss the point-like particle in the presence of the potential, but the potential will have the following symmetry. So it will be let's say separable. I have the piece which only depends on the radius, and there will be the piece which only depends on the angle theta, on the azimuthal angle, and there is no depends on the polar angle. Okay, so then once I perform the Hamilton-Jacoby, I write Hamilton-Jacoby equation, of course, and there, since my Hamiltonian is time dependent, I can perform the separation of the variables, and after doing so, I will end up with the following equation on the Hamilton characteristic function W. Okay, and this is very similar to what we've done in the class for the harmonic oscillator last time. Okay, so in here, the constant which I use for the separation of the variables, I mean, we know that it's energy, but I will just denote it as alpha for simplicity. All right, so now I have this equation, the partial differential equations, which I need to solve for W. And W is a function of r, theta, and phi. Okay, so it's a pretty complex equation to be solved. Okay, here I only will the first thing I would like to notice is that the phi variable is cyclic. So as you can see in this Hamiltonian, nothing depends on phi. Okay, phi is cyclic. What does it mean? That dh d phi equals to 0. But it also means since p dot phi is proportional to dh d phi, well, proportionality is just -1 factor, right? Proportionality factor just -1. So that means that p phi, the corresponding canonical momentum, is just a constant, right? It's just a constant. And since it's a constant, let's remember that what was the physical meaning of the W, right? The physical meaning of the W, we derive the following equations, that the W equals to pi times qi dot dt. So that's the equation we derived last time. Okay, so and therefore, if I only consider the cyclic coordinate here, it is p phi times phi dot dt, I can always pull p phi factor out of this integration because p phi is just a constant. P phi is just a constant. Okay, and what I will end up with is just the integral of phi dot times dt. Well, this integral is simple to find, right? It will give me just phi, well, up to a constant, right? So the W part which is only carries the dependence on the cyclic coordinate phi will be very simple. It's p phi times phi. Okay, where p phi is a constant. All right, and additionally, so this I will explicitly include when I write this function. Okay, and additionally, using the separation of the variables logic, I will assume that this function, that I have a function which only depends on the radius, and there is a function W2 which only depends on the theta. Okay, substituting this ansatz into this equation over here, and separating the everything which depends on r and everything which depends on theta, I will obtain the following equation. Okay, the following equation. So here sometimes I write E, sometimes I write alpha. So this is the same as alpha. Oh, give me a second. So, apologies. So this is actually E. So, and I will use E instead of alpha here. So this is actually E, and alpha is some other constant. Okay, so now what I have, so the other constant alpha here, okay, here, came from the fact that I'm performing the separation of the variables in this equation over here. Okay, so now I needed to perform this calculation. All right, so I have now a set of two differential equations which I can, integrate and find the corresponding function w1 and w2. So schematically, I wrote this over here. Schematically, I wrote it over here. Okay, sometimes somehow I'm missing something. Okay, I got it. So this is also alpha. This is also alpha. I introduced beta in the beginning, but then I decided to switch it back. So I will use E, okay, and alpha in this way. Okay, now everything should make sense. All right, so now I can write my entire Hamilton principal function as, okay, it will have this trivial component which is given by minus E times T. Okay, the other trivial component which corresponds to the cyclic variable, and these two non-trivial integrals with respect to r and with respect to theta. Okay, one can continue solving this problem. We can presume that, for example, Q1 is given by E, Q2 is given by P phi, and just we deselect some constants, and Q3 is given by alpha. Okay, and we will be able to find that corresponding capital momenta P1, P2, and P3 are, well, as you remember, they are just constants. We developed this we wrote this Hamilton-Jacoby equation in that way. And after this, we can express, using these equations, we can express little q's, or in other words, these little q's are my set of r's, theta, and phi. We can express them in terms of the constants pi and qi's. So these are my qi's, and pi is the other set of the constants. Once I've done this, I will also be able to find p1, or p phi, p theta, pr using the corresponding equations, etc. So essentially, it's just following the logic of how we did it for the harmonic oscillator last time. Okay, so this is. But here we have some non-trivial step that after separation of the variables involving time and space, we still have to perform another separation of the variables over here, where we selected the piece which only depends on r and the piece which only depends on theta. Okay, so this is why it's non-trivial. All right, so and in your homework, you will have another non-trivial example of the same. In the homework, you will have a separation of variables in z and x directions.